Hello everyone, today I'm gonna show you how we can create this effect. It's all done on texture using the camera view vector. This is the node setup, the basic node setup. You can add a lot of stuff to it, but this is the main principle. It's not that complex, but you can create some cool stuff with it. This is what I have a render view of it, like something spacey and kind of a ring, and like a ring. So yeah, let's dive into it. So we create the geonode first. As always, we will create a copnet. I'm also gonna start out with a sphere. I'll start with a sphere. We can give it like 25 or 50. Set this to the z-axis. Then do a UV texture on the z-axis and polar. So we have a sphere with correct UVs, but maybe fixed boundary seam. One thing about this effect is you need correct, or like UVs on your mesh, and also camera position, like a camera for your view. It doesn't work in perspective unless you can use like the perspective camera itself. I'm gonna do a null here, out sphere. Then we can dive into the copnet. First we'll start out with creating the camera position. We can do it here. Then we create the soap geonode. We go inside, do an object merge, select our camera origin here, so you need to click on this. Then into this object, then you can see here we have a position, and if we would move our camera, it updates. So this is the camera position. Okay, so then we have this, we'll name this camera pos. So we have the camera position here. Then we'll link this position to our constant. So what we can do is do point, then go to our camera pos, the object merge, then 0, because it's only one point number, 0.0, p attribute, and the x, and we can copy this and do here 1 for the y, and here 2 for the z. So here we have the same numbers like here. So this is the camera pulse rasterized basically. Okay, so now we have our camera. Then we also need our position of our mesh. Let's do a sub import mesh pos. We create the sphere here, out sphere. Then we rasterize the setup and convert it from position space to UV space. So we get this, and then rasterize geometry. Here we need the orig p. It's the original position that gets created there, and it's RGB, and then also the normal. Then we can create a null here. Then we need to subtract the position from the camera position, normalize this, and this is then the incoming vector. View material. This is like the incoming vector, so based on your camera we get the vector with different values where it's coming from. Also need to do a multiply, so brighten this with this is like how deep we want to get it, so let's say 7 for now. Then the important part is we need an invoke block, normal block, and in this block a vector that will confirm. So we'll go from a vector to a distance, or like a mono value. This is like the main building block of this effect. What the invoke block does is it references what is between this and acts like a kind of function. So I can reference the block end here, so drag it into this and set inputs. We get the same as this. When we do an invoke block here with the position, you can see it changes based on our camera position. This just references to this. What we need to do in here, create a constant 3. I did it with OpenCL because I think I got some weird issues. It's just multiplication, it's nothing complex. What we need is bind layer, then bind layer const a float, and then we can click here. This can RGB, and then also this RGB. then we can just multiply it, and it's here times const. Then we can do a fractal noise 3D based on that position. We need to divide it again by this constant, and then we can do it into the block end. Okay, this is the issue I'm getting when doing a multiply. The thing that background is missing, so I did it with OpenCL. So yeah, I needed to restart because for some reason I didn't update this. But you can see when I changed my camera now, it updates the noise. We can make it a bit bigger. And my original file I used the Perlin, set to something like this. Okay, so now we have the noise, but it's still just noise and no 3D effects. So what we need is we need to use this invoke block to add noise to our incoming vector and add that to the position map. So I'll show you how we do that. We need again a block with an ray origin name and the ray direction. The ray direction is the camera vector, or yeah, like the incoming vector, and the ray origin is the position. So this is the direction, and then here is the incoming. Also need both of them here. Okay, can connect these up, make this smaller. So then we need to, first of all, on the ray origin position, we need to do the invoke block and then multiply the ray direction with this value. So you can see it's basically like this multiplied with noise. So we create a different kind of depth into our position map with this, and then we add this value back with our original position map, and that becomes the ray origin. And then if we create multiple iterations, that's where the effects starts to come, because we iterate on the same position map but add noise back onto it. So for the second time we do the noise with the invoke block, we use an already noised up position, and that causes it to create this effect. But for some reason, not viewing the ray origin, we get this, but we still need to subtract the original position map from it. Ah yeah, I didn't have the iterations on. You can see we get this 3D effect. All of the art direction comes from here. Let's do 2K. Like this is where you create most of the effects. You can even go with pixelated values. You can do some very cool stuff with this. But let's set it back to Berlin. Yeah, maybe 1. The annoying thing is that it's like if you move your camera like this, it doesn't update. You need to let loose. But what you can do, for example, is set your camera here, then keyframe it, maybe set it to 120, move it to here. So we have a camera animation. Then we can also do a quick constraint for the camera. For look at, select object we want to look at. We have this motion, so then in our copnet we can play it and it does update. So this is like the base of the effect. We can then even do like a length. So this is like the 3D noise, and then for example if you want you can do a curvature of that, or like blur it or pixelate it. You can do a lot with this again. But the thing is, now we don't have normals yet. So for the normals, we also need to do an other setup with a block. But first, let's clean this a bit up. Then if we change this here, it's also like how deep it goes. Like if you have -2, it's only a bit. But if you have -15, it's like a lot of detail. 5 for a basic effect. We'll color this yellow because it's the invoke block. These are our vectors that we're shooting. This is the position, and this the incoming vector. So these are like the startings, the middle, the invoke. So for the normals, we need the ray origin. Let's create a null here. Ray origin. We need a block again with a few parameters. We need 4 in total, a vector, that's gonna be RGB, the position, so RGB, then the iteration number is a mono, and then that's it. so we can remove this one. The P is the ray origin. Let's also create them here. Vector, ray, origin, and iteration, mono, RGB, RGB. We can already connect them all up. Then we need to create a constant for the vector that starts at 0. And for the iteration, it should also start on 0. For the iteration, the only thing we need to do is do an add and then a constant of 1, so we know which number of iteration we're on. We only need 4 iterations. This is like a set amount because we need to do it for the x, y, z, and then a white value to create the normals. So let's start. We need to use the iteration, convert it from a value from 0 to 4 to 0 or 1. So when we get like iteration 0, it's 0, then 1, 2, 3, 4. We get a different value. So when we do a ramp RGB here into the position, concentric, R, G, B, and then white, we need to create constants of this. Then also I've had some issues with, I think it's a floating issue of the numbers, that if it's exactly 0.25 and this is also on 25, then it like glitches and not gives the correct color. It mixes them even though they're set on constant. So I just do minus 0.01. So yeah, now we get like red, green, blue, white. This will be like our axis. Then we need to multiply it with 2. Oh, constant. And add -1 to it. So we like, it's like if it's red, the red will stay red, but the green and blue value will become -1. So we have that. Then need to multiply this vector with 0.05, and then we need to add this vector together with our position, and then on this position we again need to do the invoke block to get the distances, and then multiply this with the axis, and then add our vector on top, and then this will become the vector. So first we do like the red value, then the green. So iteration 1 is going to be the red value, do the math on it, then multiply this with the noise, and then add it to the vector. So then we will have our red values and minus green and blue values because of the -1. Then we do it for the green, add it back on top of that vector, and then do it another 2 times in total. So if we normalize this, you see we do get values even though it's pretty dark here. So if we can't use it here in the preview material because it's world space normals, but you can use it in shader because that's how Houdini. We will go maybe into a lobnet quick, sub import material library, Karma material builder. Then we can directly plug this into the normal, set it to vector, and use op geo1. Okay, so then first create a null for this so we know where it's at. Null out world space normal out world space normal. To be sure, set it to raw, then assign it the sub import. Then when we go into render view, so scene import cameras, then we can see it here with the normal. So if you do like an environment light with a red texture, this is what we get. Maybe this is not the best. Sure, so then these are the normals then. Yeah, so then basically we have a position here. Here we get the depth, you can call it. This is like how deep the vector goes, like the white is where it's like starts getting foggy. You can also use this as like a thing in your material that's like kind of fog thing. Just play around with it, I guess. But one thing I will still show is if you want mask for like flat parts, then we can do the invoke block here on the original position and then compare if it's greater than 0. So then you can do like this mask, and if you multiply it, for example, with the world space normal just to visualize it, it's like these are the flat parts and this is the inside. So yeah, then we get this effect. If you want it on a rubber toy, for example, you can just do rubber toy. It has UVs, nice. Then you can come here, go into the camera and see the magic happen. There's one problem here where we can see the UV seems a bit, but it should be possible to fix that with using extrapolate boundaries maybe. Yeah, if we do extrapolate boundaries, it already fixes it a bit. Then you can play a bit with these settings, I guess. Yeah, then we fixed most of the UV seams, I think. And then you can start creating maps based on these attributes we have. So the world normal would just be the normal, but then you can even use the word normal for like a curvature that you get like this. Or you can start using different noises like alligator. The only thing you need to play with the center quite a bit for most of them, and maybe also the element size. Different effects, and yeah, then you can start adding more noise to the noise position, like here. Create a purlin, just be careful with the amounts you add. Create a purlin or like multiply this with a constant of like 0.1 here, or like 0.1 to make it more stretched. And yeah, you could it's just basic vectors and adjust them how you want it. So yeah, that's the very base of the setup for how to do ray marching. I also want to credit Celestial Mates on Instagram, because this is where I saw the effect for the first time and it was done in Blender. So credits to him. And I saw his setup and recreated it in Copernicus. So yeah, thanks a lot for watching.